Continuing in Chapter 3, Section 1, now let's look at quadratic functions. Our objective is going to be to graph quadratic functions, and we're going to be given two different forms of a quadratic function from which to graph. All right, we can see a quadratic function in what we call a general form, or we can see a quadratic function in what we call a standard form. And we've had practice with both of these forms, but maybe not so much with graphing with the general form. So in a previous lesson in section 2.5, we did look at the standard form of a quadratic function when we were doing some transformational graphings on those parabolas. All right, a little more background. A quadratic function has degree 2. The shape is a parabola. Every quadratic function has an absolute max or minimum. Because all three of these parabolas open upward, they all have an absolute minimum, lowest y value. Had these parabolas open downward, then those parabolas would have an absolute maximum, an absolute highest y value. So every quadratic function has an absolute maximum or a minimum, not both. The highest or lowest point on the graph, and that is called the vertex, the turning point. Every quadratic function has symmetry about the vertical line that runs through the vertex point. And the equation of this vertical line is called the axis of symmetry. We have a mirror image when we fold along that vertical line. All right, so we've got three graphs here that we're going to connect to when we look at the two different forms down here. So let's just make sure we're familiar with these different parabolas here. So we have y equals x squared, which is this graph right here, where the vertex is centered at the origin, 0, 0. So in the equation that results in this graph right here is y equals x squared. All right, now we still have a quadratic function. We have a high exponent of 2, but notice that we have a subtraction of 4 with the x. So from our 2.5 background, we knew to take this common function, the parent function, and shift it right 4, which that's the result of moving this graph to the right 4 and getting this graph right here. So notice the vertex of this new graph lies at 4, 0. This has an absolute minimum, of 0, y equals 0 at this turning point. All right, and this third and final graph right here, it's kind of hard to see, but this third and final parabola right here is the result of graphing this quadratic function. Well, from our previous work, we can see that the parent function is y equals x squared, but we're shifting right 4 and down 5. So come back here to y equals x squared and think about taking this kind of important point here and moving it right 4 and down 5, and now putting your vertex for this new equation at 4, negative 5. Okay. Each of these three parabolas have a line of symmetry. For y equals x squared, okay, right here at x equals 0, that's the equation, x equals 0 of this vertical line. If we were to fold along this y-axis that has an equation x equals 0, we would have a mirror image. Well, x equals 0 is not the line of symmetry, the axis of symmetry for these other two graphs, because I've shifted them to the right 4. So let's look at just this parabola right here represented by this equation. Okay, right here at the vertex, I'm going to draw on this vertical line. So I'm going to dash it. If I were to fold along this vertical line, I would create a mirror image of both of these graphs. And the equation of this vertical line always begins x equals, and it's the x coordinate of that vertex, which is x equals 4. So both of these parabolas have an axis of symmetry whose equations are x equals 4, because when you fold along x equals 4, you have a mirror image for these two right here. So this negative 5 had no effect on us coming up with the axis of symmetry. All right, so our main objective is to take these two different forms of quadratic functions, and based on some things that we're going to do, we're going to be able to produce a graph of those quadratic functions. This one's going to be the easier one because we've had background with that, with transformations. This equation in this form, this general form, this quadratic function, we're going to have to do some other things to kind of identify certain key places on the graph of the parabola that's determined by that equation. And we'll get there. All right, down here towards the middle is some information about each of these two forms. So here's information about the general form, and here's information about the standard form of a quadratic function. Okay, we'll start with what's familiar. We'll start with the standard form. Okay, so we have 3 examples here. So in example 1, we're familiar with f of x equals x squared. It's this graph right here. Okay, it tells us up here that the standard form of a quadratic function, they're using, notice that how we have different letters of the alphabet. We have like H and K, where we're used to having like A, B, and C. But when we have a different form called the standard form of a quadratic function, we don't use those same letters other than A. We use the letters H and K to represent what we call the vertex or the turning point of the parabola. So here's the standard form right here, again repeated. Okay, we're told that H, the value that falls behind the subtraction sign, H, comma, K, this is the number we're adding or subtracting outside the parentheses, HK is your vertex. So in this case, it would be 0, 0, like right here. The axis of symmetry we saw was x equals 0. The axis of symmetry is always the equation x equals whatever the value of h is. Well, for our example for f of x equals x squared, remember the vertex is 0, 0. So that means that h is going to be 0. Our axis of symmetry is x equals 0. Another way to write f of x equals x squared is if I were to take that understood 1 right here and put it outside of parentheses. Notice if I put x minus 0 and squared it, that still results in just x squared. If I added a 0 and cleaned all this up, I'm still getting x squared here. By writing f of x equals x squared in this form, I can see h and I can see k. So h here and k here, the origin. Right, and we've just identified that a is 1, h is 0, and k is 0. All right, let's go to the second equation right here, f of x equals quantity x minus 4 squared, which is this graph right here that's been transformed. Let's see if we can identify a, h, and k from this equation. Remember, a in the standard form is the coefficient, the number in front of the parentheses. I see h is 4, it falls behind the subtraction sign. Okay, now I don't have a k value that I see, but I can add that kind of fake little plus 0 in there. So h is 4 and k is 0. So a is 1, 4, 0. So the vertex is 4, 0. Let's confirm that 4, 0 is indeed the vertex of this parabola, and it is. So what was the axis of symmetry? What's that vertical line that creates a mirror image? Well, it's x equals h, or 4. All right, let's look at example 3, where we've done a couple of transformations on the parent function. So a is 1, h falls behind the subtraction sign. Now we do have a value for k right here, and we're going to call that negative 5. So you might be thinking, okay, well, you know, we take kind of the opposite of what's in the parentheses, and you're right. So had this been x plus 4, then h would be negative 4. But we literally take this number right here and put it down as our value of k. It's our shift up or down. So our vertex is 4, negative 5. Our axis of symmetry is x equals h, which is x equals 4. And we'd already looked at that up here, so hopefully this makes sense why we're getting what we do here. All right, so we're going to be doing some graphing of some quadratic functions. If that quadratic function's in standard form, we're going to be looking at the vertex and plotting it, and we're going to be looking at identifying the axis of symmetry. All right, a lot of background, okay, before we get to the graphing, the main part. But we need all this to connect to when we go to graph. Okay, so what happens when we have the other form, the general form? Notice there's no parentheses. You know, we do have a square, but there's no parentheses involved. Okay, this form right here is a little more difficult to identify what the graph of the function looks like, because I don't identify any kind of transformations, left, right, up, or down. Okay, well, what this general form is going to do for us is it's going to allow us to find the vertex, but we've got to do a little bit of work. the x-coordinate of the vertex, okay, or the h, if you will, and the k here. The h is found by identifying the opposite of the b value and dividing it by 2 times the a value. It's kind of like the upfront part of the quadratic formula. To get the y-coordinate of the vertex, or the k value, we're going to insert whatever number we get here for h first into the original problem to get the y-coordinate, or sometimes called the k, okay, that belongs to the vertex. All right, and something I mentioned earlier when we were looking at some graphs on the other sheet was, what's the y-intercept? Well, the y-intercept is easy to identify because remember, the y-intercept means that all x coordinates are 0. So if I go to the given equation and everywhere I see x, okay, I plug in 0, I'm going to be left with just the constant. So the y-intercept will always have the ordered pair where x is 0, and then the y-coordinate, or the y-intercept, will be that number that doesn't have that variable x with it. Okay, for the general form, let's go ahead and start with the common function of the parent function. I could rewrite this common function as 1x squared plus 0x plus c. So let's identify that a is 1, b is 0, and c is 0. Okay, now using this formula up here to get the x-coordinate of the vertex, I'm going to take negative b and divide it by 2a. Let's think about what that would be. Well, the x-coordinate is equal to the opposite of 0 divided by 2 times a, or 1. Well, x equals 0 over 2. Well, 0 over 2 is just 0. Now to get this k-coordinate, or y-coordinate, I'm going to take that 0 that I found, and I'm going to go back to the equation and plug in that x for this x right here, and the result would be another 0. So the vertex for the parent function, the common function, should be 0, 0. What's the y-intercept? Well, let's let x be 0. So if x is 0, y is 0. It makes sense because the origin is still the vertex and the y-intercept is still at 0. Okay, let's do a little more complicated function right here. In general form, we identify a to be 3, b is negative 12, and c is positive 1. So what's the vertex? Well, I've got to take that formula. The x-coordinate of the vertex is opposite b, so that would mean that's going to turn to a positive 12 divided by 2 times 3, or 6. 12 divided by 6 is 2. So I'm going to put 2 here. How do I get the y-coordinate, or the k, that belongs to this vertex? Well, plug 2 back into the original problem. And all that work is done right here. When you plug 2 into your calculator, you're going to get negative 11. All right, so the vertex is actually going to fall at negative 11. Now, I don't have a graph of that. These don't correspond to this equation. This is a different equation with different graph. But anyway, the vertex would occur to the right 2 and down 11. Okay, and the graph would open upward because this a value is positive. What's the y-intercept? Well, y-intercept, oh yeah, that means x is 0. So go back to the equation. If x is 0 here and x is 0 here, I'm left with just 1. So the graph of this parabola will cross the y-axis at 0, 1. That's a lot of information. We're going to try and pull it all together, and our purpose here is to graph some quadratic functions, whether we're given the functions in standard form or general form. All right, and just some quick other things down here. The sign of a, whether it's positive or negative, determines if the parabola opens up or down. If a is positive, we know the graph opens up. If a is negative, we know the parabola opens down. So here a is positive, so we know that parent function opens upward. Here a is negative 1, so it's just a reflection through the x-axis. That parabola has its vertex still at the origin, but instead of opening up off that vertex, it opens down. All right, one other thing that we don't really spend time on is that the absolute value of a determines the shape as it compares to the parent function. When on the parent function a is 1. So like for example, this a value right here, Okay, it's 3. The absolute value of 3 is still 3. Okay, and because 3 is greater than 1, the graph is more narrow than the parent function. So it's going to be skinnier. So if the parent function opens like this, y equals x squared, but we're talking about y equals 3x squared, it's going to be made more narrow or skinnier. That's called vertical shrinking. Excuse me, vertical stretching. That's a stretch. Like I said, a lot of our work doesn't rely on that today, but just some background about the effect of A on the graph. If the absolute value here of 1/3, which it's already positive, is just 1/3, and A is a number between 0 and 1, the absolute value of A, is between 0 and 1, the graph is made more wide. So if this is the parent function right here, and I'm multiplying by a absolute value of A that's less than 1, greater than 0, then that graph would be wider. That would be called a vertical shrink. Like I said, most of our work doesn't deal with that, but it's good to know if my graph is going to be skinnier or wider, and the effect of that is based on the absolute value of A. Okay. All right, let's get busy. Let's go and let's do some graphing. All right, this is standard form, this is general form. Depending upon the form that we have, that will determine the different things that we find so that we can then use that to assist us in sketching the graph of these quadratic functions. So first of all, we want to decide if the parabola opens up or down. That would be determined by the value of A. Then we want to find and plot the vertex. In standard form, the vertex is easy to identify. It's HK. In general form, the vertex, we have to do some work by using this little formula to get x, and then taking that and plugging it back in to get y. After we find the vertex, we might want to find and plot the x-intercepts by letting y equal 0. That was the first lesson. And then we might want to find and plot the y-intercept. We just let x be 0 and then figure out in the equation what's left, and that's going to be our y-intercept. Sometimes those might not be enough features to help us sketch the graph. We might want some other points to assist us. So what we can do is just choose some x values to plug into the original equation to get some other ordered pairs that are on the graph. Okay. All right, here's our first example. So here's the quadratic function, and we want to sketch a graph without a calculator of what this parabola looks like. So these are some things that are going to help us determine a pretty good graph of what that parabola looks like. Okay, so first of all, notice that we are in standard form. So I'm just going to write the standard form above it. It helps me memorize all the variables. So A is the number in front, and then I have x minus h, quantity squared. Quantity means you'll see parentheses, and then plus k. That's the formula. It's right here. Okay, first thing I might want to identify is that A is equal to, in my problem, A is equal to 1, which is positive. It's greater than 0. So the graph opens up. So first thing I notice is the graph's going to open up. Can I find the vertex pretty easily? Yep. The turning point is going to occur what falls behind the subtraction sign. That's 1. And then literally what's outside the parentheses, that's 1, -2. Now again, had this been in parentheses x plus 1, then I have to take the opposite of that positive 1 and put a -1 here, but I would still keep this -2 here. All right, what is the axis of symmetry? Well, in standard form, if you go back to the previous page, the axis of symmetry is vertical, x equals, and it's always the h value. All right, I'm going to go now and start to build this graph, and then I will come back here and let the graph help me determine what some of these answers are. So the first thing I'm going to do is I'm going to locate the ordered pair, 1, -2. I see my grids didn't show up good. Okay, so this is 1, and this is -2. So off of this vertex at x equals 1 and y equals -2, I want the graph to open upward. So I'm going to lightly sketch in an upward opening parabola. I do know the axis of symmetry is at x equals 1, so I will draw in that dashed line. maybe label it x equals 1. All right, so corresponding points have to be the same distance away. So if I'm talking about this ordered pair right here on the graph, then this horizontal distance away from this axis of symmetry needs to be the same amount on the left-hand side of this axis of symmetry. So that's why I kind of lightly sketched this in, because I might have to come back and kind of tweak this a little bit. And besides, I just roughly sketched where I think this graph cuts through the x-axis, but I need to know exactly what these x values are, these x-intercepts or real zeros. All right, what's the domain? Oh, well, that's all real numbers. From what I have in place, can I get the range? Yep. The range, the absolute minimum occurs at y equals -2. Okay, and then the graph opens up. So the y values start at y equals -2 and go upward. We have an absolute minimum. And the way we report that is, for me, I'm just going to do the ordered pair, 1, -2. So the minimum is y equals -2 at x equals 1. So I'm not sure how MyMathLab asks for the absolute min or max, but either ordered pair, or if it asks what it is, the absolute minimum is -2 and it occurs at the x value of 1. Do I have any x-intercepts? I do, and I will find those. So I'm going to come down here and use this space. So the x-intercepts are when I let f of x be 0. So let me write the equation down. So on that first lesson that we did, the review, we let f of x or y be 0. Now, we never encountered a situation kind of like this where we had to FOIL or anything on the previous lesson. So I'm not going to FOIL this out, multiply it out. I'm actually going to use the square root property. I'm going to add 2 here and add 2 here. And I'm going to keep this binomial squared like this. I'm going to trade sides. Because now I'm going to bring in the square root around that whole quantity. So in standard form, this is kind of the procedure I use when I'm finding the zeros. I don't do all that messy algebra. I just get the constant to the other side and bring in the square root. All right, so the square root undoes the square. We bring out x minus 1, but remember, put all of that in absolute value. This will not simplify, so just bring down square root of 2. Remove the absolute value. Adjust with the plus minus. Write out 2 solutions. Oh, let me back up here. Let's add 1 here. It's common practice not to put this constant behind the square root, but in front of the square root. So I'm going to just kind of line it up here. X equals, now putting all this together in a row, I'm going to have the positive 1 up front, plus minus square root of 2. Remember, that means x equals 1 minus square root of 2 is your smaller answer, and x equals 1 plus square root of 2 is your bigger answer. Well, this isn't really going to help me so much. I need some decimals to figure out where I'm at on this real number line. Square root of 2, I don't know. So I'm going to go to my calculator, and I'm actually going to type this all in, and I'm going to get -0.4. Now, I just rounded to the tenths place because, I mean, if I got even more specific, I mean, that's not going to, I just need a general area of where this x-intercept is. On the calculator, 1 plus square root of 2 equals 2.4. So these are my my solutions. So I'm going to go back to my graph now, and I'm going to go, okay, -0.4 is probably about right here. And positive 2.4 as an x-intercept is 1, 2, about right here, 2.4. So I did a fairly good sketch. And then extend your graph and put arrows on the end of it. And try and draw your parabola so that when you fold along x equals 1, these corresponding points would match up. All right, let me come back up here. Now an x-intercept, well, that means they want an ordered pair. So -0.40, and then the other one is 2.4, 0. Now, those are just approximates. I could have used these radical answers. Those are exact, but this is fine for what we're doing. All right, so these were x-intercepts. So I'd like to put the label, I should have put it up here, x-intercept up here, and then I put like a colon and I put y equals 0. Because every time I write x-intercept and y equals 0, it reminds me that I replace 0 in for the y in the equation and solve. Okay, next they want me to find the y-intercept. Well, the y-intercept means that x has to be 0. So let's pull the equation down in front of us. So everywhere we see x, we're going to replace it with 0. So f of 0 equals, that means that's your x, and then 0 minus 1, we'll square it, and then minus 2. So let's go to our calculator, and when we finish all this work, we get -1. So the y-intercept, this is function notation, but we know that this function notation means 0, -1 is a point on the graph. Let's look at our graph and make sure that it looks like we're cutting through 0, -1, and it does. That's a good enough graph for me. I mean, if I wanted to plug in like x equals -2 to the original equation to figure out what the answer is, to get another point, you can plot additional points. But for me, that's good. Not quite done. Now what I need to do is I need to answer increasing and decreasing intervals. So increasing interval is here, and decreasing interval is right here. So just kind of revisiting some old content is here. Okay, the increasing interval of x's, so from x equals 1, this is 1, x equals 1 to infinity, the graph of the function is increasing. Now remember, this is not an ordered pair. This describes a set of x's on which this graph is going up. And the graph is decreasing from -infinity up to x equals 1. And never brackets on the increasing, decreasing question, only parentheses. Okay. All right, went kind of slow on that one, but hopefully the other ones will go more quickly. So we'll do one more of these in this form, this standard form. So I'm going to actually skip 2 and 3 right now. I'm coming back to them. Okay, but let's find another example that involves the standard form. Here it is. Okay, so I'm going to write the standard form down again in front of me. Don't forget the square up here. I'm going to identify that A is 1, which is greater than 0, comma, means the parabola is going to open up. Okay, now I'm going to go and I'm going to find the vertex. Well, the vertex is HK. So remember, I don't have a subtraction sign, so take the opposite, so that'd be -3, but keep the k value of -4. In this form, the axis of symmetry is x equals the x coordinate -3. So let's come over here to the grid and let's get this vertex on here. So -3, -4 is about right here. I know the graph opens up. I don't know how wide, so I'll just guesstimate. And then I'll come back when I find the zeros and kind of adjust here. And then when I find the y-intercept, then I'll also adjust if need be here. Domain is all real numbers. The range is actually your k value, the y coordinate here. Okay, the range starts at -4 and goes up to infinity with the bracket. We do have a minimum, and that minimum is the vertex. You may be asked, what is the absolute minimum? Well, it's y equals -4, and it occurs at x equals -3. Do I have any x-intercepts? Yes, I do, based on the visual. Do I have a y-intercept? Yes, I do. I'll do that work here. Let's go ahead and take care of the increasing and decreasing intervals. We can do that based on just what we have. Increasing, I might want to not highlight it too much because I might have to tweak it. And then decreasing here, that doesn't depend upon anything other than the x-coordinate of the vertex. Okay. Increasing interval occurs from x equals -3 to positive infinity, only parentheses around this question. And decreasing comes from -infinity, and the graph stops decreasing when x is -3. Okay, they're asking me to describe the transformation of the parent function. I can do that. Go back to the original equation. I'm going to go left 3 and down 4. And I can see that when I take the parent function and move left 3 and down 4, that's exactly what I got by using the HK values here. All right, let's find the x-intercepts and the y-intercepts. So x-intercepts, that means y is 0. So I'll go back to the original equation, and wherever I see y, or f of x, I'll plug in 0. I'm not going to FOIL. I'm going to add the 4 to the other side, and then bring in the square root. I'm going to trade sides. Okay, now I'm going to bring in the square root. Square rooting undoes the square power, bring out the x plus 3, but don't forget the absolute value on that even root. Square root of 4 is a nice number, it's 2. Okay, we're removing the absolute value and adjusting to plus minus. Let's come up here. I'm going to rewrite the problem. I'm going to subtract a 3. Should I put it behind the plus minus? No, common practice is usually right up front here. So I have x equals the negative 3. I want to put this all in a row, plus minus 2. So the smaller solution is negative 3 minus the 2, and the larger solution is negative 3 plus the 2. So come back up here, I can figure this out. It's negative 5. I can figure this out, it's negative 1. So let's go to our graph. Does it appear that I have an x-intercept at negative 5? Yep, it's right here. Does it appear that I have another x-intercept at negative 1? Well, I need to tweak it and put it right here. So I'm going to go ahead and finish with a little bit more precision, like this. And I need to be mindful of where the y-intercept is too. Oh, and I meant to dash in the axis of symmetry. And that would be x equals negative 3. Okay, so reporting x-intercept, these are the solutions or the zeros or the roots, but to report them as x-intercepts, remember it'd be negative 5, comma 0, comma negative 1, comma 0. All right, the y-intercept, to remind ourselves, that's when x is 0. So I'm going to bring down the equation, but everywhere I see x, here and here, I'm going to replace x with 0. So f of 0 equals, well, that's 9 minus 4, so that's 5. So the y-intercept is going to be 0, 5. Ooh, I was way off on that one then. I guess it's way up here. So my graph will come in, hit that x-intercept. It's kind of skinny and go up that way. So I'm trying the best can. All right, we'll do one more of these in the next video, and then we'll finish with the other, the general form.